That's almost it for part 1 of On Time in Half the Time. So let's quickly recap the major points we've covered in the 6 videos to consolidate the learning and bring things together. Firstly, we talked about the 4 simplifying assumptions that SDBR makes. The market is the constraint, which means that the plant has more capacity than demand. There may be a capacity constrained resource in the plant, but there is unlikely to be a bottleneck, so lacking in capacity that detailed finite capacity scheduling is required. Touch time is less than 10% of the elapsed time, meaning that for the vast majority of time, parts or even whole work orders are in the plant, they wait in queues to be processed by work centres, or units wait for the rest of the units in their batch to catch them up. And finally, as there is no real bottleneck, we don't need an array of different buffers to protect throughput, and we can simply use one buffer, the shipping buffer, to allow work orders enough time to get through the plant, and we can dispense with all of the complicated calculations multiple buffers would require. We also learned about where SDBR shouldn't be used, that being any manufacturing process that requires sequence-dependent setups, like paint manufacture or certain types of food manufacturing process that I've worked in the past. These types of factory can lose a significant amount of capacity when they deviate from the required sequence, and this can result in huge damage to throughput. Don't use SDBR here, call a friendly TOC consultant like me instead. We also learnt about Goldrat's bathtub-shaped inventory curve, and how, when inventory is in the plant too long, it creates queues which cause a whole host of other problems to arise, ultimately resulting in chaos in the plant. Similarly, too little time in the plant, and we also experience chaos. With too little time, work orders can be delayed by the slightest glitch, and with little or no time to recover, become late. We also learnt that between the two extremes of too much time and too little time, there is a plateau of relative calm, greatly reduced queues, but also some time to make up for the inevitable things that go wrong in a manufacturing environment. We learnt about how choking the release of raw material moves a conventionally managed manufacturing plant from the chaos of the right side of the inventory curve to the plateau. To do this, we distinguish between a quoted lead time that we give to the customer and use to calculate the due date, and a production lead time, which is the time we allow work orders to be processed through the plant. They don't have to be the same thing. After taking an order and committing to a due date using the formula, today's date plus the quoted lead time equals the due date, we calculate the raw material release date using another formula, that being due date minus the production lead time equals the raw material release date. We then add the work order to the raw material release schedule and hold it back from being released to the plant until the correct date, thereby choking the release of raw materials to be only a buffer time, 15 days in the case of our little plant, ahead of the due date. We saw how this choking mechanism drains the plant of inventory in the early stages of an SDBR implementation, allowing the work centres a breathing space to clear away the queues and be ready to process new work orders that sales continues to accept through the initial choke period when the choke period ends. This combined with the buffer management priority system increases flow through the plant. The buffer management guides the work centres to work on the right work orders in the right sequence. Late orders first, orders closest to their due date next, otherwise known as red orders, then work orders in the yellow zone, and then finally work orders in the green zone. This is the only prioritization system used in the plant from now on. No cherry picking work orders, no grouping of work orders of a similar type to create economic order quantities and save setups, no targeting efficiencies and keeping people and machines busy, just follow the buffer management colors. We examined the effect of the choke period and the buffer management process after 15 days in our little plant and how inventory had been reduced and the majority of inventory left congregates in front of the CCR. We explored what you can do if there is a CCR in the plant and I explained the theory of constraints 5 focusing steps. I cannot emphasize enough how important this framework is to understanding TOC and being able to use it effectively to improve the performance of a system like a manufacturing plant. And I gave you a list of 12 different tactics you can use to increase capacity and therefore flow at the CCR, all of which were based on our understanding of the 5 focusing steps. These tactics will help eliminate the queue in front of the CCR quickly and again further increase flow through the plant, reducing the manufacturing lead time and improving due date performance. We talked about how work orders begin to be released again after the end of the initial choke period. These work orders started to flow quickly through the plant because the level of queuing had been greatly reduced. And we saw the impact of the actions we took to increase capacity at the CCR on the queue. These actions taken together are why I claim that manufacturing plants using SDBR, and indeed other types of operational processes, can halve their manufacturing lead time and dramatically improve their due date performance. And by now, you'll have no doubt worked out that this is why the series of videos is called On Time in Half the Time. We cut the time required in production by 50%, and on-time performance goes up, on time in half the time. But that's not all. We can further reduce the manufacturing lead time. In fact, in SDBR implementations I've led, we've cut the manufacturing lead time by much more than 50%, and in fact I claim 75% should be readily achievable in many plants, and I've even seen it cut by over 80% on a few occasions, with due date performance improving considerably as a result. And the mechanism that helps us to achieve this is a focused process of ongoing improvement. Excellence is a journey without end, but it can be a highly frustrating journey with many dead ends unless we have a focusing mechanism that directs us to the areas that will deliver us the greatest return on the investment of our time, effort, and money. Hence, using the buffer management data and the Pareto chart. We note which resource the work orders are waiting for when they transition from one zone of the buffer to another, and this gives us the data we need to create a Pareto chart that helps us to focus. Hence, using the buffer management data and the Pareto chart, we note which resource the work orders are waiting for when they transition from one zone of the buffer to another, and this gives us the data we need to create the Pareto chart that helps us to focus. And when we have improved to the point where a small minority of open work orders in the plant are in the red zone, this triggers us to reduce the production lead time and forces us to improve even further. But this is improvement with a clear objective. We are trying to create a very low lead time, high reliability manufacturing system of superior capability. Capability that can deliver products at speeds that few, if any, of our competitors can match and for which our customers are willing to pay.